There is a photograph in the Peterbilt archives that surfaces occasionally at industry events and in the collections of serious truck historians. It shows the instrument panel of a late 1970s conventional cab and to a driver trained on anything built after 1995. It looks less like the cockpit of a commercial vehicle and more like the control console of an industrial facility that someone has decided to operate from a seated position while moving at highway speed. Gauges everywhere. Toggle switches in rows, knobs without labels, because the driver was expected to know what they controlled by position and by feel. Warning lights that illuminated in amber rather than the internationally standardized colors of the modern era. An ashtray integrated directly into the instrument panel surround, positioned for convenient access during operation, because the idea that smoking while driving a truck was anything other than a normal professional activity had not yet occurred to anyone with regulatory authority over the industry. Every single element of that instrument panel tells a story about the engineering philosophy, the manufacturing economics, the regulatory environment, and the operational culture of an era that produced trucks that were, depending on your perspective, either the most characterful commercial vehicles ever built or the most demanding, unforgiving, and genuinely dangerous pieces of industrial equipment that working drivers were expected to operate without complaint across millions of miles of American highway. This is a forensic inventory of 30 features, systems, technologies, and design choices that were standard, common, or at least widely present in the American commercial truck market of the 1970s and 1980s, that have since disappeared entirely from current production vehicles, and that illuminate something true and specific about the era that produced them. Some disappeared because they were dangerous. Some disappeared because they were superseded by better engineering. Some disappeared because regulatory changes made them non-compliant. And some disappeared for reasons that are more complicated than any single explanation captures, because the culture that valued them, the operational context that made them sensible, and the manufacturing economics that made them feasible all changed simultaneously, and the features went with them. The first was the floor-mounted throttle that operated on a direct mechanical linkage to the injection pump, with no electronic mediation whatsoever. A driver who pressed the accelerator pedal in a 1975 Kenworth W900 was pulling a cable that moved a fuel rack inside the injection pump in direct, real-time, proportional response to his foot pressure. There was no electronic control unit interpreting his input, no torque management software moderating the fuel delivery, no throttle position sensor translating mechanical movement into an electronic signal that a module then acted upon. The response was immediate, completely transparent, and completely unforgiving. Too much throttle on a slippery surface produced wheel spin that the driver managed with his foot, not with a traction control system. The loss of that directness is something that drivers who experienced it still describe with a specificity that suggests it was a genuinely distinctive sensory experience. The second was the manual fuel shutoff valve, mounted in an accessible location in the cab or on the fuel line, operable by the driver without tools, that allowed the engine to be killed by cutting fuel supply rather than by the ignition system. This was a safety feature of a particular era's thinking, the logic being that an engine that had lost its ignition system in an accident, but whose fuel supply was still connected, presented a fire risk that the manual shutoff addressed. The valve was typically a quarter-turn ball valve or a lever-operated shutoff, and its location was standardized enough within each manufacturer's design that drivers expected to find it in a specific position. It disappeared as fuel system design evolved toward configurations where the fire risk logic no longer required a dedicated manual intervention point accessible to the driver. The third was the engine compression release, the Jake brake, in its earliest and most mechanically direct form, operated not by a cab-mounted rocker switch connected to an electronic solenoid, but by a direct mechanical spade, cable or linkage that engaged the compression release mechanism on the cylinder head. The feel of engaging a mechanical Jake brake was different from the electronic versions that followed, heavier, more deliberate, with a physical resistance in the control that told the driver exactly how much he was asking the mechanism to do. The noise it produced was also different, louder, less regulated in its acoustic character, which is why the Jake Brake noise ordinances that appeared in mountain communities and urban freight corridors were driven largely by the mechanical units of this era, rather than by the more acoustically managed electronic systems that followed. The fourth was the multiple gauge oil system monitoring array that was standard on serious Class 8 applications of the era. A driver monitoring his engine did not have a single oil pressure gauge and a warning light. He had an oil pressure gauge, an oil temperature gauge, and in some applications, a separate crankcase pressure indicator that monitored blow-by, the combustion gas leakage past the piston rings that indicates ring wear and provides early warning of developing engine problems. These gauges were not redundant. They were a diagnostic system that a knowledgeable driver could read to understand his engine's condition with a granularity that modern engine management systems, for all their sophistication, do not routinely present to the driver in an accessible format. The fifth was the pyrometer, the exhaust gas temperature gauge that was standard equipment on turbocharged diesel applications and that experienced drivers used as their primary indicator of engine load and turbocharger. Efficiency. A driver climbing a grade watched his pyrometer the way a pilot watches his manifold pressure gauge. It told him whether the engine was working within its thermal limits, whether the turbocharger was producing adequate boost for the load being applied, and whether the fuel delivery was calibrated correctly for the operating conditions. The disappearance of the pyrometer from standard instrument clusters. It is still available as an aftermarket edition, but is no longer standard equipment. On most production trucks, removed a diagnostic tool that experienced drivers considered essential and that no substitute instrument has fully replaced. The sixth was the manual choke control, sometimes called an ether injection system, in diesel applications that drivers used to assist cold starting in low ambient temperature conditions. Diesel engines of the era were significantly more difficult to cold start than current common rail engines with glow plug systems and electronically managed injection timing. The manual ether injection system allowed a driver to introduce a small quantity of starting fluid into the intake airstream to assist ignition in the combustion chamber when cylinder temperatures were too low to reliably ignite diesel. Fuel through compression alone. The system required judgment. Too much ether could produce a combustion event that exceeded the engine's mechanical design limits, and damaged pistons from ether overuse were a documented maintenance issue of the era. The skill of using the system correctly was a genuine technical competency. The seventh was the dual needle air pressure gauge that displayed both the primary and secondary air brake system reservoir pressures on a single gauge face with two needles of different colors. This instrument told the driver, at a single glance, the pressure status of both independent circuits of his air brake system. A driver who understood what he was looking at could identify a slow leak in one circuit, the recovery rate of the compressor after a brake application, and the pressure differential between circuits that indicated a one-way check valve that was not seating correctly. It was a diagnostic instrument as much as a monitoring instrument, and the drivers who understood how to read it had a genuine mechanical intelligence advantage over those who did not. The eighth was the mechanical tachometer, not an electronic one, that used a flexible cable rotating inside a housing to drive a mechanical needle display directly from the engine's accessory drive. The mechanical tachometer had a response characteristic that was slightly different from its electronic successors, a small lag and a slight damping in the needle movement that experienced drivers actually preferred because it smoothed out the momentary RPM fluctuations that occurred during gear changes and allowed a cleaner read of the engine's steady-state speed. When the cable wore or frayed, the tachometer would produce a characteristic flicker or oscillation that was itself a diagnostic signal. Drivers who felt or saw that oscillation knew they had a cable to replace before it failed completely. The ninth was the underdash fresh air vent system that operated without any powered fan assistance, simply a hinged or sliding panel in the firewall or instrument panel lower section that, when opened, admitted ram air from outside the cab directly into the interior space. In the era before cab air conditioning was standard equipment on most working trucks, this system was the primary means of managing cab temperature in moderate ambient conditions, and drivers developed skill in managing it, opening it partially to create a specific airflow pattern across the cab that directed fresh air toward the driver while limiting turbulence that would scatter papers or interfere with the state. CB radio's squelch performance. It sounds primitive, It worked. The 10th was the manual cab tilt system for cab over-engine configurations, operated by a hand pump hydraulic system that the driver worked from outside the vehicle to tilt the cab forward for engine access. This system required the driver to connect a hydraulic hose, pump the cab forward to the service position, install the safety prop rod, perform whatever service work was required, remove the prop rod, pump the cab back down, and disconnect the hose. The entire process took considerably longer than the modern equivalent of pulling a cab tilt lever inside the cab and watching a powered system do the work. But it was simpler in its mechanical architecture, easier to diagnose when it malfunctioned, and repairable with tools and skills that an experienced driver could provide without specialized equipment. The 11th was the chrome spoke steering wheel, with a diameter that would appear comically oversized in a modern vehicle context. The steering wheels on 1970s and early 1980s commercial trucks were typically 22 to 24 inches in diameter, necessary because the steering gear ratios and lack of power steering assistance on some applications meant that the mechanical advantage of the large wheel diameter was the primary means by which the driver could manage steering effort. The chrome spoke construction was a functional choice, as much as an aesthetic one. Chrome does not crack or delaminate in the sun the way plastic does. It can be cleaned with a rag, and its thermal conductivity means it does not retain heat the way a black plastic wheel does in a cab that has been sitting in summer sun. The large diameter wheel is a genuine design solution to a genuine problem, and its disappearance is as much about power steering becoming universal as about any change in aesthetic preference. The 12th was the hand throttle, also called the throttle lock, or the hand-operated cruise control. That was a simple friction-based mechanism, allowing the driver to set a throttle position and hold it without maintaining foot pressure on the accelerator. This was the working trucker's cruise control before electronic cruise control became standard equipment, and it was used in ways that modern safety systems would prevent. Setting the hand throttle and standing up in the cab to reach something on the upper bunk while traveling at highway speed was not considered remarkable behavior in the operational culture of the era. It was simply what drivers did when they needed both hands free and had no passenger to assist. The 13th was the external sun visor, the full-width chrome or painted steel visor that projected forward from the windshield header and shaded the driver's field of view in low-angle sun conditions. These visors were effective enough at their design function that they created a characteristic shadow pattern on the windshield that experienced observers could use to estimate a truck's time of manufacture from a distance. They disappeared for aerodynamic reasons. The external visor created a significant drag penalty at highway speeds that the post-fuel crisis efficiency environment could no longer absorb, and their functional replacement, the internal adjustable sun visor, is demonstrably less effective in the specific low-angle sun conditions they were designed to address. The 14th was the underhood engine access that was a full-width opening on conventional cab trucks, allowing a standing driver to reach essentially any component on the top of the engine without lifting panels, removing shrouding, or navigating the crowded accessory drive architecture of modern emissions-compliant engines. The 1970s diesel engine under a conventional hood was laid out with a spaciousness that reflected both the mechanical simplicity of the pre-emissions era power plant and the design philosophy that assumed the driver would perform basic service work himself and needed the physical access to do so. Modern engines under modern hoods are not designed for driver-level service access. They are designed for dealer-level service access with specialized tools and diagnostic equipment. The 15th was the mechanical fuel injection pump, the inline or rotary injection pump that metered and delivered fuel to the injectors through a purely mechanical system of springs, cams, and governor weights that required no electrical power to operate. A mechanical injection pump diesel will run as long as it has fuel and compression, regardless of the status of the electrical system, the battery, or any electronic control module. This characteristic produced a reliability in remote or off-grid operating environments that modern common rail diesel systems, with their dependency on high-pressure electrical fuel supply systems and electronic control, cannot match. Old-school operators who used mechanical pump trucks in environments where electrical failures were real risk-logging operations, mining, remote construction treated the mechanical injection system's electrical independence as a primary reliability attribute. The 16th was the split-shaft powered takeoff that was a factory-installed or dealer-installed option on many 1970s and 1980s Class 8 tractors, allowing the truck's transmission to drive auxiliary equipment, hydraulic pumps, generators, refrigeration compressors from the driveline rather than from the engine's front accessory drive. The split-shaft PTO allowed auxiliary equipment operation at variable speeds corresponding to the transmission output speed, which in some applications provided better operational characteristics than the constant speed engine accessory drive. It also allowed heavy auxiliary loads to be driven without the parasitic loss penalty of a front mount accessory drive operating continuously, because the split shaft unit could be disengaged when auxiliary power was not required. The 17th was the mechanical speedometer cable, a flexible shaft rotating inside a housing that translated wheel rotation into needle movement on the speedometer face without any electronic signal processing. The mechanical speedometer had a characteristic response, a slight oscillation at certain speeds caused by cable harmonics, a tendency to read slightly optimistically at highway speeds due to the calibration tolerances of the mechanical drive that drivers learn to interpret and account for. When a mechanical speedometer cable failed, the failure was immediately obvious and the replacement was straightforward. An experienced driver could replace a speedometer cable with hand tools in under an hour. The 18th was the vertical exhaust stack, positioned immediately behind the cab, typically in twin configurations on either side of the sleeper or single stack on the driver's side, with a rain cap that opened under exhaust pressure and closed when the engine was off. The vertical exhaust stack's positioning directly behind the cab created an acoustic experience in the cab that modern horizontal aftertreatment systems do not replicate. The exhaust note from a twin stack configuration at full throttle was audible inside the cab in a way that connected the driver to the engine's operational state. The rain cap's characteristic sound on startup, the metallic click of the cap lifting under exhaust pressure, was a sensory confirmation of engine startup that experienced drivers used as a secondary verification that the engine had fired correctly. The 19th was the mechanical refrigerator, more accurately, a passive cooler or icebox that was standard equipment in the sleeper berths of many 1970s and 1980s long-haul trucks. These units used either block ice, which drivers purchased at truck stops and fuel stops along their route, or in more sophisticated configurations, a eutectic plate system that absorbed and stored cooling capacity during periods when shore power or engine-driven refrigeration was available, and released it during the off-engine rest period. The eutectic plate system in particular was an elegant passive thermal management solution that preceded and in some ways inspired the battery-cooled cab air conditioning technology that is now being promoted as a novel solution to passive cablet plate solution. The overnight cooling problem. The 20th was the in-cab fuel tank sight glass, a transparent tube mounted on the instrument panel or the cab interior wall, connected to the fuel tank by a small diameter line that showed the driver the physical fuel level in the tank without requiring a sender and gauge system. The sight glass required no electrical power, had no moving parts that could fail, and provided a fuel level reading that was accurate to within the diameter of the tube rather than subject to the sender calibration drift that float-type fuel gauges routinely develop. Its failure mode was a cracked or discolored tube that reduced readability, a condition that was immediately visible and that required nothing more than a replacement tube to correct. The 21st was the cab-mounted gear shift pattern diagram, a physical plate or decal mounted in a visible location, showing the shift pattern for the specific transmission installed in that truck. This seems like a trivial detail until you understand the context. A driver in the 1970s might regularly operate several different trucks with different transmission configurations. A 1-0 speed in one unit, a 1-3 speed in another, and 1-8 speed in a third, and the shift pattern for each transmission was genuinely different in ways that required conscious reference when switching between units. The gear pattern diagram was not a concession to driver incompetence. It was a practical operational tool for drivers managing multiple equipment types. The 22nd was the mechanical fuel primer pump, the small hand-operated pump mounted on the fuel filter housing or the injection pump itself that allowed a driver to manually prime the fuel system after a fuel filter change or after running the tank dry. Running the fuel system dry on a mechanical injection pump diesel required the driver to manually pump fuel back through the system to purge air from the lines before the engine would restart. The manual primer pump made this a driver-level operation that could be performed at roadside without tools or assistance. Without it, the same task required either a service call or disassembly of fuel system components to introduce fuel manually. The 23rd was the adjustable steering column, not in the tilt and telescope manner of modern adjustable columns, but a column that could be repositioned in multiple planes during a service interval, requiring deliberate adjustment with tools rather than in-cab micro-adjustment by the driver. The logic was that once the steering column was positioned correctly for a specific driver's ergonomics and confirmed to be in that position with fasteners, it was stable in a way that continuously adjustable columns are not. Drivers who had their column set correctly reported that the fixed position produced less fatigue on long runs because the steering wheel position was absolutely consistent rather than subject to the small shifts that loosely adjusted. Telescoping columns can develop over time. The 24th was the engine-driven hydraulic power steering pump that operated continuously at a rate determined by engine speed rather than by steering demand. The power steering pump in a 1975 Kenworth was pumping fluid through the system at highway cruise speed, whether the driver was turning the wheel or not, producing a continuous parasitic load on the engine that represented a measurable fuel economy penalty. Drivers who understood this sometimes made routing decisions, avoiding routes that required significant parking maneuver, steering inputs based partly on the awareness that heavy steering demand was mechanically costly in ways that modern variable assist and electric power steering systems have eliminated. The loss is not the technology. It is the operational consciousness that the technology's transparency created. The 25th was the cab-mounted engine brake control that required the driver to physically select both the activation switch and the intensity level through separate controls rather than the integrated rocker switches of modern systems. Some configurations required the driver to enable the engine brake through a switch on the dashboard, set the intensity through a separate rotary control, and then activate it through the fuel pedal liftoff rather than through an automatic throttle off engagement. The multi-step engagement process was deliberate. It prevented inadvertent engine brake activation in conditions where sudden deceleration was inappropriate and required the driver to consciously construct the complete operational configuration rather than simply switching on a preset system. The 26th was the cab air horn pull cord, a physical rope or cable mounted at a convenient driver reach point, routed to the air horn valve on the cab exterior, that operated the horn through direct mechanical linkage without any electrical intermediary. The pull cord horn had a response characteristic that differed from the button-operated horns that followed the driver, could modulate the horn's duration and intensity through the force and speed of the pull, producing a nuanced range of horn expressions that experienced drivers used with genuine communicative intent. The standard short-long-short pattern used as a passing acknowledgement, the sustained blast used as a grade warning, and the rapid repeated pulls used as an emergency warning all had distinctly different feels in the pull cord version that the button-operated equivalent does not replicate. The 27th was the physical map pocket, a large format document holder mounted in a visible driver-accessible location that held the paper maps, route sheets, and delivery instructions that governed the driver's navigation of an unfamiliar route. These were not standard glove compartments. They were purpose-designed document management systems, sometimes occupying an entire panel section of the cab interior, with enough organized capacity to hold the multiple map sheets required for a transcontinental route, together with the delivery paperwork, weight tickets, and fuel receipts that the driver was required to maintain. The physical organization discipline required to manage a long-haul route's documentation in the pre-GPS era was a genuine professional skill that the navigation application has rendered unnecessary, and in doing so, removed from the competency development path of the current generation of drivers. The 28th was the mechanical engine governor that limited maximum engine speed through a purely mechanical system of weights and springs inside the injection pump, a system that the driver could feel in a distinctive way. As he approached the governed speed limit, the engine governor in a mechanical injection pump application produces a characteristic throttle resistance as the governed speed approaches. The pedal becomes progressively harder to depress further as the governor mechanism resists additional fuel delivery. This physical feedback gave drivers an immediate, intuitive sense of where they were in the engine's operational envelope without requiring them to monitor the tachometer. The governor's feel was different between manufacturers and between governor settings, and experienced drivers could identify the governor specification of an unfamiliar truck within minutes of operating it based on the throttle feel alone. The 29th was the manually operated sliding rear window in the sleeper cab, a simple aluminum-framed glass panel that slid horizontally in a track to provide ventilation in the sleeping compartment without powering any electrical system. In warm weather conditions, where active cooling was unavailable, the combination of the sliding rear window and a small battery-powered fan created a cross-ventilation airflow through the sleeper that was genuinely effective at maintaining sleeping temperatures in ambient conditions up to the Donder under Avires, mid-80s Fahrenheit. The sliding window required no maintenance beyond occasional track lubrication, had no failure mode beyond physical damage to the glass or frame, and provided a ventilation function that the fixed, sealed windows of modern sleeper cabs designed for integration with powered HVAC systems cannot replicate without powered assistance. The 30th, and in some ways the most symbolically significant, was the individual truck character that resulted from the combination of all the preceding features operating together in a specific configuration that was unique to that unit. That particular installation of that particular engine with that particular transmission in that particular cab with that particular driver's personal modifications and maintenance history accumulated over years of operation. A 1,978 Peterbilt 359 with 400,000 miles on its original 400 Cummins Big Cam, broken in by its first owner on the Seattle to Los Angeles lane, and then sold to a flatbed operator in Texas who had adjusted the governor, installed a specific aftermarket exhaust configuration, and replaced the original steering wheel with a wood rim unit. He preferred. That truck had an operational character that was as individual as a fingerprint. No other truck felt exactly like it. No other truck sounded exactly like it. The driver who knew it could tell its condition from the sound it made at startup, from the feel of the steering at highway speed, from the way the clutch engaged at the bottom of its travel. Modern trucks are more reliable, more efficient, safer, and more comfortable than anything the 1970s and 1980s produced. The data on every one of those dimensions is unambiguous, and the improvement is real. But they are also more uniform, more electronically mediated, and more thoroughly removed from the mechanical transparency that made the old trucks simultaneously more demanding and more personally connected to the people who operated them. The features disappeared. The trucks got better. Both of those things are true, and the tension between them is the honest history of how the industry moved from one era to the next.